Okay, the first topic in quant being the correlation and regression. There is some amount which has been covered in L1 also with respect to correlation, but here L2 being more focused towards calculations and application. So we may have to take up some data, do some kind of calculation. So what I am doing is parallelly I am putting up an Excel sheet also to demonstrate how we actually calculate all these things and how do we interpret it. So I'm taking a live data, and based on that we are trying to drive this entire concept. And most of the time, most of our concepts will be driven through that mechanism itself, whether it is FRA or any of the other stuff. So the initial part in this being a scatter plot of the data, where when I want to talk about a correlation or a regression, it's more about the interaction between the two variables. Are they moving together in the same direction? If one is going up, is the other also going up, or is it the opposite direction, or no relation at all? So that is obtained through a simple scatter plot, trying to plot the two data items. Let's say here I am taking a data items right from Jan 05 till Jan 13, the quarterly share price of a company versus the earnings of that company. 1 year, 1 period lag, 1 quarter lag earnings. So I would like to do a scatter plot between these two data items. Now doing a scatter plot is actually in this case is telling me, it is giving a relationship between the X value, which is the share price, and the Y value, which is the lag. And in this case what we are observing is, it looks like a 45-degree straight line. From the origin, it is looking like a 45-degree straight line. A 45-degree straight line will give me an indication that both as X is increasing, probably Y is also increasing. To a large extent, we are able to observe that as X values are increasing, the Y values are also increasing. But in some cases, we may observe a pattern that as X is increasing, Y could be falling. Or we could observe a pattern that even if X is increasing, Y may or may not be changing at all. Or in some cases more, some cases less. So based on that, we arrive at what is the relationship between the two variables. So scatter plot is one of the diagrams which help us in finding out the relationship between the two variables. The more it is aligned with a 45-degree straight line, the more I say it is positively correlated, or the more it is a minus 45-degree line, I say it is more strongly negatively correlated. But the more the flatter it is, horizontal it is, I can go with there is no correlation existing, right? And we have found out using a formula also how do I find out correlation. We have used it in our earlier cases, where we said correlation for a sample is nothing but x minus x bar into y minus y bar divided by n minus 1. So here also on this data, let's say if I am trying to find out, n minus 1 is for a sample, and in most of the cases in a real world we work only on samples. So that's where we'll have n minus 1 only for finding out the correlation or covariance, right? So we are going with x bar. So first thing, just as a quick refresher, the x bar is trying to come out with a simple average of the values, average of x, and y bar coming out as average of y. So here I am taking y as the 1 period lag earnings and x as the share price. Okay, so I am taking average of 1 period lag earnings. So this is what it is. Now I want to find out x minus x bar into y minus y bar divided by n minus 1. So going with it, x minus average of x, then I'm taking y minus average of y. So here every element of x minus the average of x. This is what I do. All right. So I am doing it for every element of x. I am doing it with respect to the average of x minus average of x. Similarly, I am doing y minus average of y. So I am taking this as y minus average of y. So every element I am subtracting from the mean. That's how we are doing with our. So x minus average of x into y minus average of y divided by n minus 1. So that's where I'm looking at the multiplication of those two, x minus average of x multiplied by y minus average of y, and all these things are being summed up. So that's where I am looking at covariance in this case as nothing but the summation of x minus average of x into y minus average of y divided by n minus 1. So here n in our case is 33 observations, or probably I am starting from the second row. So there are 32 observations. So minus 1 is making it 31. So which is arriving at the covariance being 2,86,000. Now this covariance, the next question that comes up is it high or low? Covariance as such does not have any boundary. Yeah, it ranges from minus infinity to plus infinity. So there is no base for me to say whether it is high or less. So from that standpoint, only the sign matters. They are positively they have a positive movement. I can't say how strong is that movement, right? So from that standpoint, a correlation has been introduced, which is simply the normalization part of the covariance, which is nothing but covariance divided by the standard deviations of both of the variables. Now when I am taking the standard deviation of x, or as well as the standard deviation of y, just as a process, it is nothing but each x minus x bar, whatever we have done, I can do the squaring, right? X minus x bar, the x minus x bar square, which is coming out to, this is my x minus x bar square. Same way I do y minus y bar squared. All right. Now my standard deviation is nothing but x minus x bar squared into x minus x bar squared add up divided by n minus 1. So that is where here I am taking the square root of x minus x bar squared totally added up, which is the summation of x minus x bar squared divided by n minus 1, which is 31 again in our case. So in this case it is saying the standard deviation of x is around 343 units, and similarly the standard deviation of y is coming out to this divided by 31. All right. So the standard deviation of y is coming out to 1348. So based on the multiplication of these two, covariance divided by the standard deviations of both these elements is giving me the correlation. So in this case it is coming out that the correlation is 0.61. So we know that the correlation lies between minus 1 to plus 1. So probably 0.61. Now the question comes out, is 0.61 a high correlation or a low correlation, right? So that is where I need to have some kind of a basis to test whether this correlation is high or low or no correlation. Is it negative? Is it high or low or not even no, or even no correlation? Yeah, it lies between -1 to +1. Probably if it is 0.3, can I say is it is existing or not existing? If it is 0.8, should I say it is high or low? Again, it should not be subjective there. It has to be, it's not relative. I have to test out whether it is high or whether it exists or does not exist. So just like any other hypothesis testing, we will do a hypothesis testing for the correlation also. So whatever number comes up, it could be 0.61 here, but when I calculate based on some other sample, I may get 0.3, I may get 0.2. 0.2, I need to know whether it is equal to 0, which means that 0.2 is it by fluke? Because some other sample I take, it may become 0 or it may become -0.1. So is it by fluke or is it consistently 0.2? Is it significant? So from that standpoint, just like the way we have done hypothesis testing for means and variances, we have to do a hypothesis testing for correlation also. So the test that is typically used for the correlation aspect, I'll come back to all these things. The test that is typically used for the correlation aspect is a t-test, where I use this formula r into square root of n minus 2, n is your sample size, r into square root of n minus 2 divided by square root of 1 minus r squared. That is the t statistic which we are using. So r is nothing but the correlation. So whatever, if it is 0.2 or whatever are the numbers. So in this case, let's say I am taking whatever we got through our sample calculation, 0.61. I put this into the formula. Look at it with n minus 2 degrees of freedom. Whether it is at 5% level of significance or 1% level of significance, I can define my business rule. Now putting the same, my t-test is nothing but r, which is 0.61, into square root of n minus 2, n is 32, so n minus 2 is 30, divided by square root of 1 minus r squared, 1 minus r squared. So this is telling me that the t value is 4.3, which is the t statistic for our computed value. For our case, the t statistic is 4.3. Now I have to say whether this, based on this t statistic, whether the correlation is significantly different from 0 or can I take it as 0. So the null hypothesis in this case is correlation equal to 0. Alternate is correlation not equal to 0, right? So from that standpoint, we are trying to find out for 30 degrees of freedom, what is the t value. Probably in your case, he will give it directly in the question itself. What could be the t value, in either in a table form or directly a value being specified, or because the sample size is more than 30, you can very well assume the numbers closer to normal distribution. 95%, so probably you can take it as 1.96 directly, right? So because the t value is lying outside the limits of -1.96 to +1.96, we will reject the null hypothesis. If the calculated value lies between -1.96 to +1.96, we are going with the null hypothesis. So which means correlation equal to 0. If it is lying outside the limit, we are rejecting the null hypothesis and simply going with correlation not equal to 0, which means it is significantly different from 0. So 0.61 means it is existing correlation. Whereas, let's say just for example, I get correlation as 0.2. My t value is only 1.11. Which we have to go with the null. We cannot reject the null. We are failing to reject the null hypothesis. So we are saying in that case, if the correlation is 0.2 also, according to me, it's nothing different from 0. Right? That 0.2 is a fluke. Just because of the sample which we have taken, that 0.2 is coming. It's nowhere different from 0. So even if it arrives to, let's say, 0.3, probably the same scenario. So 0.3 also is as good as 0 itself. So to say at what point it changes, or when should I take it as significant, it depends based on this test. If my sample size is very small, probably the t-value, the correlation should be very high to say it is significant. If my sample size is very large, probably even with a smaller correlation value, I can say there is a significant correlation. So that's how we are looking at the correlation. So in this case, t value is 4.3. So we are directly saying there is a significant correlation existing. And in this, every correlation depend on the graph. It could be, if it is showing more on a 45-degree line, I am saying more or less it is correlated strongly. A minus 45-degree line more or less correlated negatively. But the real test is finding out the t-test. And in this data, if at all I came across that x and y are correlated very strongly. Now what is the intention of finding out that correlation? Using that y, I should be able to find out x, or using x, I should be able to find out y. So I have to make these two variables in such a way that one is a dependent variable on the other. Just by knowing one, I should be able to predict the other. That is where, based on the correlation, regression is coming into picture. The moment I am saying regression, the correlation coefficient plays a very significant role. The moment I find out r and r squared is nothing but it's nothing to do with the correlation there. R squared is the coefficient of determination. Now, what does it explain? Here, if I look at a smooth line here, if I look at a smooth line, there is a lot of variation of the points across the smooth line. So that variance, by what extent it is explained by my smooth line. So when I try to find out the variance of all these points, and I try to find out the variance of each point with respect to a line, by what extent is it different? One, I find out the variance of all these points, a simple variance, x minus x bar whole squared by n minus 1. Then I find out another variance looking at every point, the difference from the line. That difference, I find out the variance. We'll do that. Once we get a line, we'll try to do that. And that tells me if most of the difference, if most of the variance of my original data is present as a part of the regression line also, then it means that the explanatory power of that variable is much higher. So if I am using x to predict y, right, I am trying to find out the variance of y in isolation. I am trying to find out, using x, one formula to find out y. That formula of y, I will try to find out the variance. Like if I say y is equal to 2x plus 3, some formula came out to me. Now, based on the original data of y, I will try to find out the variance of y, which we have done in our case. Now, I will use the formula of 2x plus 3 and compute y. Now a new set of y's are coming. I'll try to find out the variance of those new set of y's. If I see that the variance of the new set of y's is more or less equal to the variance of the original y's, I say that there is a lot of explanatory power. There is a lot of deterministic power in my estimate. My estimate is a pretty strong estimate. The reason why I don't want to link it with correlation here is when we have multiple variables, here we are only talking about x and y. But the next thing which we would be looking at is x and y1, y2. In those cases, correlation is a word which I should not use. The reason being, correlation is always between two variables. But there we'll have three variables. So correlation will not be the word to be used. That's where we use it, though we compute it as r squared, but we still call it as explanatory power of the variable. Now, how strong is x in explaining y? Which is nothing but explaining in sense the variance of y, how much is it incorporated in x? The more it is incorporated, we say that the determination percentage is much higher. We'll try to compute the equation, and based on that we'll try to look at the goodness of the fitness of the model. The higher the value, the better is the usage for the prediction purpose. Now in this case, okay, let's complete this and go there. Now correlation, whenever I am trying to find out between two variables, there are three major limitations which we come across. One is, if my data has outliers, one or two values, the mean will get affected. The mean affects it, and probably the whatever x minus x bar which we are using, that is getting affected. So correlation is getting affected. Only for one heavy extreme outlier, you will find that the correlation is very badly affected. Instead of 282 here, I just make it 82 or something. Correlation is directly getting impacted. Okay, here 0.61 was becoming 0.62. Whereas in some cases, if I make it, let's say instead of 1001, I make it 10,001. We will find, you see, correlation suddenly dropped to 0.24 from 0.61. So one extreme outlier present in the data can actually, even our graph is getting completely different, right? The relationships are getting badly hurt. So that is what we are talking about, outlier. Very high value or very low value can impact our correlations very badly. So the one major thing we have to do as a part of our analysis is, if there is any outlier in the data, better eliminate them. Two, there is a concept of spurious correlation, which is like, probably best example is, I take the sales of my company and I take GDP of Uganda. Try to find the correlation. I may get 0.7, 0.8 because my sales are growing, Uganda's GDP is also growing. So the correlation analysis may say there is a very strong correlation between these two. Whereas from an economic standpoint, there may not be any kind of a relationship between the two variables. That is what we attributed to spurious correlation. The data wise, because we are just taking two different data, number wise I may get a very strong value. If both are growing, obviously the age of the person and GDP of something, they keep growing. But so the correlation may still show a positive value. But in reality, there is no relationship between the two variables. That is what is the spurious. And there could be a scenario where we may have non-linear relationship. Correlation explains only the linear relationship. For example, if I have a square relationship, like I'll take a few values, -4, -3, let's say up to 1. These are my x values. And y values, I am directly taking them as the square. So 16, 9, like that I am taking. So these are x, these are y. When I try to find the correlation between these two, logically speaking, we know they are very strongly related, right? But when I am trying to find out the correlation between these two, I can use even the correlation formula in Excel to find that out. So the correlation between these two, it is directly giving 0. So correlation can actually explain only the linear relationships. If it is a square or a cube or a square root kind of relationship between two variables, correlation cannot explain. So it is directly giving 0 is the correlation here. So correlation is a funda that is applicable only to linear relationships. So probably when someone says correlation is 0, the first thing which comes to our mind is, oh, they are not related. The word we have to use is they are not linearly related. They could still be related, just like this example. They are not linearly related, right? So this is the test which we are using for doing the testing for the correlation, whether it is equal to 0 or not. Then once we know that some relationship exists, we are trying to predict. And that prediction is coming through a concept of regression, where we are creating an equation typically of this form. We are creating an equation of this form. B naught y is some b1 times x plus some constant. That is what, so which is nothing but a linear relationship between x and y. Some 2x plus 3, right? That's a kind of a relationship I am trying to create between x and y. The reason being, I should be able to predict y the moment I know x, when I know that they are correlated. So how do I arrive at these things? The arriving of these things can happen through two equations again. The b1, which is the coefficient of x, is nothing but the beta, which comes out by your covariance divided by the variance of x. The normal beta which you are using in equity relationships, the concept of that, even CAPM, RF plus beta times RM minus RF, is actually coming from this regression relationship equation itself. So the coefficient of x in any kind of this linear relationship is nothing but the beta. So if I simply look at the covariance, so in this case, if I try to find out the coefficient, which is nothing but, when I say beta, the covariance between the two divided by the variance of x. Variance, I do have the standard deviation, so I'll square it to arrive at the variance of x. So beta is saying 2.42 in this case. So in my equation, it's as good as the b1 is 2.42. So y1 is b naught plus 2.42 times x1. Now, how do I get b naught? The b naught is arrived using this, the b1 is the slope. b1 is the slope coefficient, which comes out as covariance of xy divided by your variance of x, which could be your slope. You can call it as a slope coefficient, or you could call it as beta. The terms are, again, finance term is the beta, the statistics term is a slope coefficient for that. Regression coefficient, b1 is a regression coefficient for x1. And the way I arrive at b naught is, I'll take average of y. So assume that instead of y1, you take y average. Y average equal to B naught plus B1 times X average. Right? The average value also should lie on that line. So instead of y1, y2, y3 all observations, what we are saying is y average, which we have already computed, is equal to B naught times B1, which we know now, B1 times X average. So the only unknown in that case is B naught. From that B naught, I should be able to find out what is the value of B naught. So y average, so if I want B naught in this case, I am simply taking it as y average, the average of y, right? Y average is equal to B naught plus B1 times X average. So minus B1 times X average will give me B naught. Minus B1 is nothing but beta times X average. This is what is my number. That gives me the value of B naught. So in simple sense, this equation is nothing but y, which is I've taken the 1 period lag earning as y. So this equal to B naught, which is 2156 plus 2.42 times the other variable x, share price. So if I want to take it the other way, share price I want to take it, so here it matters which one is x, which one is y. Right? Let's say if I want to predict y based on x. So x is my independent variable, y is my dependent variable. Now when I am trying to find out beta also, it should come out as beta is coming as covariance of xy divided by the variance of x being the dependent, x being the independent variable, right? Now when I am trying to find out B naught, again y average minus the B1, which is the beta times x average. Now I have the equation now, y equal to 2156 plus 2.42 times the x average. So now the same thing, now here the next part is 2.42 significant? See, we have used a formula to find out 2.42, but is 2.42 significant, or is the equation itself, which is y equal to 2.2156 plus 2.42 times x, is that equation is a good fit model or not? Is that model a good fitting model or not? Right? That is what we have to test out. So just like the way we have tested correlation, we have to test out the regression coefficients also. That's how everything which we find out using statistical formulas, they undergo a statistical test, right? So even this B1 has to be tested and the whole model has to be tested, whether the output is whatever the formula we are using for predicting, whether it is significant or not. Now in the same case, just if I change x and y, roles of x and y, we'll see a completely different values. If I make share price as x and the estimates share price as y and the earnings as x, my betas, so equation, it depends completely on which is x and which is y. Right? If I am trying to find out, let's say B1, assuming the x is, so whatever is y now, if I assume it as x, now my beta is completely different. My beta is coming out only to 0.15, and as we know, the beta has nothing to do with a high or low, right? And we can also find out the B naught, which is nothing but now the y average, which is now the x average is what I'll take. X average minus B1 times the y average. Y average, earlier y average, which is the current x average. Now if I interchange the roles of x and y, this is the number. Now I can very well say stock price, probably this could be a better equation in real world also. Stock price is equal to 119.58 plus 0.157 times the previous period earnings. So whatever the earnings that came out in the last quarter, based on that I am predicting the stock price for the next quarter. Right? Now, is this equation good enough for prediction? Some equation came out, but is it good enough for prediction? And is 0.15, is it significant or not? Two things which we have to look at here. And for that, again a t-test. Right? The t-test again in case of regression is B1 equal to 0, which is my null hypothesis. B1 not equal to 0 is my alternate hypothesis. And the way I test out is B1, whatever the value we got, divided by the standard error of B1. And from our perspective, we don't need to compute the standard error of B1. We get the value for the standard error of B1. So the table, there is a tabular values that come out. The way the table that come out is what we call as ANOVA analysis. ANOVA table. We'll just try to get the table. Even from your exam standpoint, you will get that kind of a table. Here I am taking the y is whatever I have considered as x. Let's say this is the y. I consider this as x. Then I am trying to find out a table. This is the table which is very important for us from our exam standpoint, whether it is for simple regression or multiple regression. This table is presented in most of the cases for us. Now in this, the moment we understand the relationship between all these variables whichever are specified here, most of our understanding is clear. Now you see correlation we have already computed. We got it as almost 0.61 only. That is the traditional way of computing the correlation. Even this system has given us correlation is 0.61. And one major thing to look at here is the equation. This is what is the coefficients we got just now. 120, okay, slight adjustment, 126 point something and 0.157 being our slope coefficient, right? And now I have to say whether this number is significant or not, correct? So from that standpoint, we get the standard error of the coefficients. This is our standard error. For this case, the standard error is given as this much. The calculation of the standard error of the individual coefficients is a complex process which is outside our scope. So the standard error is typically given. Now the t-test which I perform is nothing but the coefficient divided by the standard error. So that's what has come out to 4.3. Now if I do it also, the coefficient divided by the standard error of the coefficient, which is telling me 4.3 is the coefficient t statistic. And as we said, lying outside the minus 1.96 limit to plus 1.96. So we are rejecting the null hypothesis of B1 being equal to 0. So we are simply saying B1 is not equal to 0, going with the hypothesis of even though the coefficient is 0.15, it is significant. Which means the first stage is I can use this equation for a predicting purpose to a decent extent. This variable is a decent enough variable for using. The moment I am seeing this being 1.1 or 1.2 less than modulus 1.96, less than, absolute value is less than 1.96, then I can very well go with a null. So though there is a 0.15, I can very well consider it as 0. If I am considering it as 0, obviously it's like y is not dependent on x, because b0 plus 0 times x. So y is nowhere dependent on x, right? Okay, now I have this equation. The other thing to interpret here is the same relation can be interpreted from the p-values. P-value, as we have got earlier also, it's a specific, the probability up to which you will accept your null hypothesis. Now, the simple logic from this case is correct. So, the simple interpretation is, if at all I am having a p-value is 3%. I got the p-value, let's say, as 0.03. It means, if I take it into percentage, 3%. Make it as confidence interval. Take this as significance level. 3% significance level. 97% will be the confidence interval. Now what we are saying is, if this p-value is less than 0.05, if whatever the calculated p-value is less than 0.05, reject it at 5% level of significance. Reject the null. P-value less than 5%, reject null at 5%. And if P is greater than 5%, fail to reject null. So without doing any calculation, just by looking at the p-value, you can say whether I should reject the null hypothesis or fail to reject the null hypothesis. 95% confidence level. 95% confidence. Correct. So in case we are going with a 99% confidence level, we will check whether P is less than 1%. So it is like when I say P is, let's say, 0.4. In the intercept case, we got P as 0.4. So the simple way to say is, at 40% level of significance and above, my null is getting rejected. The smallest percentage at which the null is getting rejected. So in this case, if my confidence level is 100 minus whatever 0.01%, which is 99.99%. If my confidence level is 99.99% and above, then I will fail to reject this null hypothesis. Or if my the level of significance is 0.01% and below, either way you can look at confidence or significance. So if my level of significance is 0.01% and below, or level of confidence is 99.99% and above, then I will accept the null hypothesis. Otherwise I am rejecting the null. So as a simple ballpark, you just find out what is your significance level. 1%, 5%. Check whether P is less than that. If P is less than that, you are rejecting the null hypothesis. If P is greater than that, you are failing to reject the null hypothesis. So in this case, without computing this T and comparing it with the critical value and all, just by seeing these P values, I should be able to say whether I should reject the null hypothesis or not. So sometimes he will not give the table values. He will simply give this is the P value, and based on that you may have to take a decision of rejecting the null hypothesis or not. For what value? See, if I test out, okay, the simple way I'll tell you. If I find out the T value corresponding to this 0.0001%, that p value, that level of significance. If I take 0.0163% level of significance, and what is our degrees of freedom? 31, because the observations are 32. At 31 degrees of freedom, if you see, our table value is 4.28, right? Slightly if I increase, let's say 1.65 or something, decrease 63, slightly more. Now what we are seeing here, the table value is actually 4.31, the critical value. Critical values are minus 4.31 to plus 4.31. Now your calculated value is 4.3. It is lying within that interval. If it is lying within that interval, you have to go with accepting the null hypothesis or failing to reject your null hypothesis. Right? Whereas when you are going with 5%, you are actually checking the t value corresponding to 5% level of significance on 31 degrees of freedom, which will be probably 2 point something. Whereas your calculated value is 4 point something, which is lying outside. So at what area under the t curve is this 4.30 falling into the acceptance range? Right? So this is nothing but a t equation. The t curve, which is more like your normal distribution curve, slightly flatter than your normal distribution curve. Using the equation for the t, you will arrive at these values. Alright. Now, the linear regression, whatever the equation we have derived, it's actually based on a few assumptions. The assumptions are, the independent variable is not random. So what we have taken as an independent variable here, the earnings of the company. So if the earnings of a company are completely random, then linear regression has no meaning. They should not be random. They should be predictable. 2, it should be uncorrelated with the residuals. Very important aspect. The independent variable is uncorrelated with the residual. Now, how do I find out the residual? Let me go back to the sheet again. Now we know these are the coefficients, right? Now, which means the way I look at it is, in case I take the x's which are existing and based on that find out y, using this equation 126 plus 0.15 times every x, I'll get my new y's, right? That y's are based on the regression equation. Okay, so let me go back. So I have, so these are x and y's. I'll insert one more saying regression y, which is coming out as that using that equation. So I'll take the equation as 126 plus 0.15 times the x. X in my case is this number. So based on that, I'm trying to find out what should be the y. Based on if I'm using the regression equation as a substitute to y, what should be the value of y? So this is the value of y. This should be the value of y. So 455 should be the value, which means my regression value is 455, whereas my actual is 282 only, right? But this is the best possible equation which the system could identify, right? In some cases, the numbers might be very close. In some cases, they may be very far off also, right? Here, if we are seeing, okay, this is 575, whereas this is 481. And similarly, this is 868, 890, this could be 1001. So this is the closest thing which our system could identify. Now this is based on a regression estimate, right? Now if I try to find the variance in this, now this is, I can find out the variance of these y's, and if the variance of these y's also is more or less same as the variance of my original y's, then I am saying regression model is a best fitting model, is a good fit for explaining the original y itself. Whereas if they are widely different, then it means my r squared is much lesser, and probably I may have to think through some other model. Now here I'll try to find out the residual. Residual is nothing but your regression y minus your original y. Now the assumption which your linear regression is saying is independent variable is uncorrelated with the residuals. So the independent variable is the C column. It should be uncorrelated with the residual. So when I try to find out the correlation between those two, I should get it very close to 0, right? So when I try to find out, let's say the residual is coming out as the actual, the regression y minus the actual y. So these are my residual data. I'll try to find the correlation between the actual data and the regressed y data. The actual independent variable, which is x, so the correlation with the residual, it comes out for me as, when I am trying to find out the correlation, 1 between the residual and between my independent variable. Only if this exists, linear regression is valid. Okay, so if I am trying to find that out, this number you see, into 10 to the power of minus 16.000005, which is almost, even if I apply my test, it will go with the null hypothesis itself. So it is this is getting applicable. Independent variable is uncorrelated with the residuals, and residuals should be independently distributed or random in nature. I should not find any kind of pattern in the residuals. Even when I try to plot a graph with the residuals, it should be completely random. No pattern of something going up, something going down continuously. No pattern should be obtained with respect to the residuals. There is no pattern. Sometimes up, sometimes down, and no specific pattern with the residuals. So as long as there is no specific pattern, we can very well go with using a regression equation. But the moment I see sometimes up, again down, just like your technical analysis, if you observe some valid patterns, then probably it's like some other variable is also existing apart from x1. Probably I should look at x2 also and try to do the relationship of y with both x1 as well as x2. That is where we get into multiple regression, right? So as long as it is not the case, no patterns are observed with respect to the linear, with respect to the independent variable and the residual, we can still go with using the simple linear regression itself. And the expected value of the residual term is 0. Try to find out the mean of this residual term. Average of residual, it should be very close to 0. The expected value of the residual term should be very close to 0. Again, you see a very small value. to the 10 to the power of minus 14. So the expected value of the residual is also 0. And the variance of the residual should be constant, not 0. Constant even if I increase my data. Now I have 32 records. If I add 20 more records, even with 52 records, the variance should be more or less constant of the residual, not with the data. Right? So these are some of the important aspects when I am framing a regression equation. So we are getting an output of a regression equation, but the calculation of that output is based on these set of assumptions. So the tool or even the exam will give you the table directly, the ANOVA table which contains intercepts and all. But there could be kind of questions which talk about which of the following is an assumption, or X has made this statement, Y has made this statement, which will talk about the assumptions, and directly saying who is correct versus who is wrong. So for those kind of questions also, it is essential to have an understanding of the assumptions. Even if you can mug them up, that should be fair enough. Otherwise also you can test it out with the data in this format. Now the regression coefficients, we have already arrived at them, the finding out the regression coefficients, and finally saying whether it is significantly different from 0 or not. I am going with the t statistic, just like the way we have done this exercise. So t statistic is greater than 1.96, so we are going with the alternate hypothesis. So the value is significant. Now, how do I interpret this ANOVA table? This table is a very significant aspect for us. So these things we have analyzed. Even these we have looked at. The other part of it is the interval, the confidence interval, the 95% confidence interval, which is nothing but the average, the actual value plus or minus the t value times the standard error. Right? So here I am taking it as whatever is the t value here. Let's say I am going with a 95% confidence level, which is 5% significance level. And when I am going with a two-tailed test, the 5% significance level for me at 31 degrees of freedom, the t value is 2.35. Right? So just like the way we do the value plus the sample mean plus or minus 1.96 times the standard error, here I will do plus or minus 2.35 times the standard error to arrive at my 95% confidence interval. So which is coming out as 0.15 plus 2.35 times the standard error, which is 0.24 something, or if I take it as 5%, yeah, 2.232, which is what is my upper limit. And same way if I do 0.15 minus 2.03 times the standard error, which is giving me my lower limit. So what is saying, the t value for any kind of sample for 95% of the samples which I take will lie between 0.08, the coefficient will lie between 0.08 to 0.23 for 95% of the observations, which means it will not be 0 because there is no sign change. If lower limit is negative and upper limit is positive, then it means 0 also is a part of that range. Then I will say this is not significant. The variable is not significant. So I will go with null hypothesis there. So there are 3 tests for the null hypothesis. 3 ways to test out whether I should accept the null hypothesis or reject the null hypothesis. One is using the t statistic, one is with the p value, one is with your interval. So if the interval contains a 0, I will go with null. If the interval does not contain a 0, I will go with alternate. Which means I will reject the null. So in this case, the interval does not contain a 0, 0.08 to 0.23. Interval does not contain a 0, so I am going with the alternate. All three of them will give the same decision. They are different ways of presenting the same test. Because in exam, probably he may give one of those data itself in one of the forms, asking you to find out the remaining, or asking you to give the final conclusion. Now, so this table is more or less clear, right? These two things we won't compute. The standard error, we get it directly. Fine. The next table for us, the specific table, which will talk about how strong is our regression equation. First thing to look at is again a p-value. The p-value here is less than 0.05. When I am looking at 5% level of significance, this number is less than 0.05. Which means this f value, the probability comparing to this f test, if it is less than 0.05, I am simply saying model is a good fit. Probably it's like, so two conclusions which we are making. First, I look at this number, say that the model is a good fit. Here I look at these variables, say the variables are also good enough. Especially it works when you have multiple variables here. Here we are talking of only one as an independent. But if I have three, what can very well happen is, here I will say the model is a overall good fit. Whereas one or two of those variables here, they may be having a p-value greater than 0.05. I may have to go with the null there. For that variable, it's like full model versus independent variables, different independent variables, right? So it may so happen that full model is a good fit, whereas independent variables wise, they are not a good fit. That could be a problem with multiple correlation, which we will see in the next one. But in case of single, hardly we will find both these values will be more or less the same. More or less they will be the same. So if from here I am going with the alternate hypothesis, here also I will go with the alternate hypothesis, saying the model is a good fit model, right? And in this, what are the remaining things? How did I arrive at this number itself? For that, we have found out one regression equation, right? Based on the regression equation, we have computed our regression y. So there are two things which we will take up. The residuals we got, I'll do the residual square. Residuals we have computed, so I'll do the residual square directly. Residual square, which will work out to the square. When I sum up all the residual squares, that is what will be my, let me sum up all the residual squares. Sum of all the residual squares is coming out to this number, 2258 something. Now if I see here, 2258 is being present here. So the residuals, it is nothing but sum of squares of the residuals. So people call it as error sum of squares or residual sum of squares. Those are some of the words being used. So the residual sum of squares is this much. And when I say regression sum of squares, I'll try to find out the variance of the regressed wise. The variance with respect to the regressed wise, I'll try to find out, which is nothing but whatever the regressed y, whatever is the regression y we got, I'll try to find out the variance of this, or I'll try to find out the sum of squares of this, right? So let's say average of regression y is coming out as the average of this E column. This is my average of the regression y. Now if I want sum of squares, again from each y, I subtract this average value and square it. So sum of squares from each regressed y value, I subtract the average regression y value and then square it. And whatever the sum I get of all these is what will give me a regression sum of squares. So there are two sums of square, which is the total variance. We are breaking it into two parts. One contributed by regression, one residual, which is not contributed by regression. Contributed by regression, how am I finding out? I am finding out the y based on the regression equation and trying to find out the sum of squares of that. So when I am doing the sum of squares of this, it simply comes out to me as let's say 1458. This is the number that is coming out. So here we see some small difference. So 1397 being my regression sum of squares, whereas 2258 being my residual sum of squares. Now I need to really find out, is there any difference between these two? Right? If there is a difference, it means that regression is different from residual. But if there is no difference, so regression and residual are more or less the same, which means regression is nowhere powerful. Right? So for doing that, we are finding out the mean sum of squares, which is nothing but the total sum of squares divided by the degrees of freedom. And how do I get the degrees of freedom for regression and residual? For regression, it is number of independent variables. So in this case, we have only one independent variable, so it is 1. Whereas for residual, it is n minus k minus 1, where k is the number of independent variables, n is the total observations. So 32 is the total observations, minus 1 minus 1. So my residual sum of residual degrees of freedom is 30. So overall degrees of freedom is 31. Now to arrive at my mean sum of squares, I am doing 1397 divided by 1 and 22,000 divided by 30. So this is the mean sum of squares for regression. This is the mean sum of squares for residual. Then I am doing an F-test. F-test contains, in L1 also, F-test is nothing but variance of first one by variance of second one. So I am taking 1397 divided by 75,000, which is giving me 18.56. Again, I will compare it with my table value. The critical value, if I am assuming a 5% level of significance, right? So the F value for me, for a 5% level of significance, or 5% level of significance, assuming a 1 degree of freedom and a 30 degrees of freedom. These are the two. It says 4.17 is the table value. This value, computed value, is outside the table value itself. So we are rejecting the null hypothesis. Null hypothesis is equality between the variances of regression and residual. So we are saying no, there is no equality between the regression and residual values. The variances of regression as well as residual, they are different. So regression is able to explain the relationship between x and y in a much more appropriate model. That's where we say this model is a good fit model. And out of this, a couple of more calculations which we do generally is arriving of this r squared is nothing but the regression sum of squares, whatever we have, divided by total sum of squares. Regression sum of squares divided by the total sum of squares is what is your R squared. So again, in most of the questions which I have observed in this are a lot of excess would or blanks would be given in this equation. I mean in this table. You have to try to fill in the blanks using the appropriate calculation. So that's how the relationship between all these values need to be understood. So R squared comes out by that. And of course, in case of one element simple regression, you take the square root of that, you will get R. You take a simple square root of R squared, you will get the R, which is the correlation coefficient in this case. And so adjusted R squared has no meaning as far as linear regression is concerned. It's only the tool that gives the value. As far as one element is concerned, only one independent variable, adjusted R squared has no meaning. When we look at multiple regression, we look at the significance between R squared and adjusted R squared. Another thing is standard error of the entire model. Right now, standard error of each individual variable is this: B1, B0, each coefficient. This is the standard error. Whereas if I am looking at the whole model, I am looking at this number as the standard error. How did I arrive at this number? This is nothing but the square root of the mean sum of squares of the residuals. The mean sum of squares of the residuals will give me the standard error. And what we are saying with this standard error, if I have to predict my dependent variable using the independent variable, let's say for the next period, if I have to predict what would be my stock price if this is the earning. So how do I use this as my equation? I am using equal to 126 plus 0.15 times whatever is my 5502, which is telling me if I go with this assumption, my stock price need to be 993. But there is a standard error associated with the predicted value. What is the standard error? We got it as 274. So if I have to build a 95% confidence interval around it, all we are saying is whatever is my predicted value plus or minus 95%, so 1.96 times the standard error. So 1.96 times the standard. If the standard error is very, very high, we see that our limits are much, much wider. So my accuracy is not coming up that much. So it could even go up to 1530 on the higher side, or it could even fall up to 455. So what we are saying is though the value I have predicted as 993, it could very well range from 455 to 1530. That is the confidence interval, 95% confidence interval of my predicted value. Right. So this is the main thing as a part of this chapter. So ANOVA is something which we have to be very clear with. The moment you know all calculations, probably if I give some x here, right, if some of these are mentioned as x, or right, this is mentioned as x, or this is not given, or let's say this is not given, I should be able to use the other details to try to fill out these values. So if let's say mean sum of, if total sum of squares and this are given, and f is not given, I should be able to compute the mean sum of squares and then the final f value also. That's how the calculation should help us out with. So just a quick summary of the interpretations. The standard error of the estimate, which we have got it as the mean, this value, right, the square root of this value. How did we arrive at this value? which is nothing but mean sum of squares. And the mean sum of squares is obtained as sum of squares divided by 30. So that is what is the formula here. The sum of squares divided by 30. 32 was our observation. So when I do it by n minus 2, it becomes 30. So the total sum of squares of the errors or residual sum of squares divided by 30 is what is giving me my mean sum of squares. The square root of the mean sum of squares is nothing but the standard error of the estimate. So again, all these links need to be clear. And coefficients of determination also we have found out r squared, which is coming out by dividing the regression sum of squares divided by the total sum of squares. And f test also is mean sum of regression mean sum of squares divided by the error mean sum of squares. We are testing it with n minus 2 degrees of freedom. So the f value, as long as it is greater than the critical value, we are going with the alternate hypothesis. We are rejecting the null hypothesis. So as an interval, if I want to look at for the regression coefficient, as we have seen, for the predicted value, we got the value as 993. We are putting a 95% confidence interval around it by putting 1.96 times the standard error of the value. Same thing for your coefficient also you can do. If I want the 95% confidence interval for my regression coefficient, I am taking 0.15 plus the t value times the standard error. So in any case, if I want that particular coefficient interval, I am taking as the value of it plus or minus the critical value times the standard error. And the regression coefficient testing also we have done, that based on the t value as well as p value. So just as a last point in this, the limitations of the regression analysis wise, there could be a parameter instability. It's like I have taken one parameter which is the mean of the independent variable, which is the 1 year forecast, 1 year 1 period earnings. Now if the earnings go up drastically or go down drastically, my mean will become unstable. Sometimes it may be very high, sometimes it may be very low. So because of that, my regression, the whatever the formula which I have used earlier, 126 plus something, suddenly changes with one observation. That makes it as a parameter unstable. So as long as if I have to observe for more data and more or less the same equation is coming, then it becomes more like a stable stuff. Especially with all economic data, this problem will definitely arise. So I may have to focus more in terms of analysis. Sorry, come again. So identification of the probable strategies on publicly available information is always a difficult step. Sometimes suddenly if the price goes up or suddenly if the profitability goes down, it may or may not be related to the share price going up drastically, because by that time it would have got incorporated into the value. So that assumptions may get violated. The equation may get suddenly violated after a certain point in time. So every time, this is an empirical equation. This is not a scientific equation. So any empirical equation which is created based on the data, we have to keep checking it always. So that's the reason for every equation we are creating, we are doing a statistical test. We have done a correlation, a statistical test for that. We have put regression equations, a statistical test for that. We have done the final estimation, the final y value estimation, an interval for that. So it is purely statistically we are doing a conclusion, but it's not mandatory that economically this relationship will definitely exist, right?